Hey, good morning. Here's one I haven't tried or touched on very much. I've talked about radiation detectors, just muy poco, very little, focused on a Geiger-Muller tube, very specific type of tube, very specific characteristics. But I can do this with most instruments. Get down to the details of how they work, what they actually measure, and understand what they mean back. So how do you get this knowledge? How do you get this understanding? Not beliefs. I don't believe in this shit. I just understand how it works. I do take for granted some things, but I know where they are. If I need to understand them, I can go back and find them. So why this? My background, good electronics, started with tube theory and radar systems, radar sets, military sets, close combat support radar, tactical radar. Then the radar set specifically I was trained in was decommissioned and abandoned, and I got more training in another MOS. This one was in metrology, instrumentation and measurement. So basically the military taught me about how we measure everything that we can measure, why we measure it, how we measure it, who measures it, who sets the standards, why I should trust the instrument, going back to, in this case, it was a National Bureau of Standards, now the National Institutes of Standards and Technology. So a little bit of background. Deep electronics background, experience in numerous applications of this thing. So I get a job at a chemical plant as a chemical engineer. That's the title on the and the paycheck. So I did talk through them, that I have the experience equivalent to. If you notice in a lot of resumes or a lot of job ads, it says or experience. And that works. That can work if you have that experience. So anyway, Fortune 100 companies hired me to help commission, start up, and run two chemical plants, joint ventures in the same site facility. My specialty became gas chromatographs, real-time process instruments. So what's a gas chromatograph? Gas chromatograph takes gases, takes a sample, takes a bolus, takes a small bit of gas, and analyzes it for constituents. They can do elemental analysis, but typically they're doing compound analysis because the size of the compounds affects how they move through capillary columns. What's a capillary column? It's a tube full of sand. That's it. It's as simple as that. But if you push a gas through that tube full of sand, the sand will start to separate the gas into lights and heavies because the smaller molecules can get through all those little holes in the sand between the grains of sand and get out the top of the column faster. You can do this with a lot of things. If you wanted to play, you can set up a column and dump something in it and see how it separates out. Kind of like how sediment settles, only totally different, because you're using mechanical properties of whatever materials are in the columns. So as that little node of gas is pushed up through the column, it begins to separate out between lights and heavies. For conversation's sake, it's actually separating out between molecular sizes. And out the top of that column comes the lightest gases first, then the heavier gases, and then the even heaviers, and possibly a liquid. You could push, these are, you can do liquid chromatography, you can do gas chromatography, you can do interferometry. In between that, you can string these instruments together and tell all sorts of cool things. So for 3 years, I was a gas chromatograph principal in the plant. Now, I reported to an organization in another state, in Pittsburgh, and these were the expert chemists in the applications of chromatographs. And Bendix, the company that manufactured these chromatographs, also provided training, which I had. Now, most of the training in the electronics was a breeze. I'd already had it, because if you know what a Wheatstone bridge is, that's the functioning of the detector, the type of detector that's used inside most gas chromatographs. So these things were field analyzers. They took gas from the process, and it took anywhere from 30 seconds to a minute for that gas to reach the analyzer, because they were in their own houses in climate controlled environments. So that gas would get delivered. You have to know the size of the sample line and the timing of the sample to say when the sample was taken from the gas process, not when it was processed by the analyzer, because the sample can be up to 5 minutes late. So one of the analyzers analyzed plastic in the air. The process stream was plastic is a gas. Phthalic anhydride is a gas. And my analyzer took that gas and analyzed it for phthalic anhydride content and purity. So this plant facility made the most pure phthalic anhydride on the planet. It's what allowed auto manufacturers to make all the plastic fenders, because it's a highly stable, known quality plastic. So the expansion coefficients fit in well with making cars and making fenders. So that's kind of where that kind of plastic went. This is a precursor plastic that other people would buy to make more plastics of other things. So that analyzer had to work above the vapor temperature of plastic. So two of these analyzers, and these are the only chromatographs on that side of the plant. The rest were point instruments for CO2 or other gas monitoring devices, moisture content monitoring, temperatures, things like that. So those two analyzers ran an internal cabinet temperature of 280 degrees, if I remember right, because the vapor temperature for the plastic is 247 degrees, so we have to keep it in a vapor state. I had to redesign the sample lines because an engineer underspec'd the thermal requirements to keep the sample lines hot to deliver the sample from the process to the gas chromatograph for sampling. About a minute and a half delay on that sample time, then the analyzer took roughly a minute to run. So what I had to learn in the Bendix school was about columns, and I knew fractioning towers and columns, you know, the physics of them, how they work, but as applied in gas chromatography, it gets a little bit more detailed, a lot more detailed. So there I learned about molecular sieves, about capillary columns, how to pack columns, what the columns do, what to look for in the sample. I also knew that I had to go speak with the professionals at Bendix and the professionals in Pittsburgh if there were any issues with the analyzers. Because while I might be able to diagnose it, I had to peer review any changes made to make sure that they fit what we were doing. So those analyzers, once we got the sampling system worked out, ran very well. If you've ever seen the switching the gas process in a gas chromatograph in order to push that sample through columns and the way it's done, it's amazing. Lots of fun. So the other instrument house I had was measuring things like ultra high purity, or not ultra, it was high purity hydrogen, that a syngas generator. We stripped off a syngas generator with a pressure swing absorber to make ultra high purity hydrogen for later use in the process to rebuild molecules into polymers and such. So both sides had huge reactors, exothermal reactors. The plastic side was massively exothermic. Generated 600 pounds steam. That's how we kept the plastic moving around in the pipes. So you go figure the temperature of 600 pounds steam, not water, steam. So anyway, I had a chance to get very familiar with gas chromatography, separations, molecular separations, We had sample systems. One of the samples that got added because of one of my reports about a field incident was volatile organic compounds monitor out in a waste field, because we had spilt something and had to clean it up, and if it had escaped, so we had to put in an analyzer out across a field and get that one working. And that basically sampled sewage sludge, tore it up, macerated it, and pushed it through a chromatograph to look for volatile organic compounds, explosive materials, or harmful materials that could have gotten into the Houston ship channel. So that was 3 years with gas chromatography. I resigned that job to go to work programming in the nuclear facility, which is another video somewhere. And I probably could, I can't do details on that one too much, but I've talked enough to it. So after 3 years of maintaining those gas chromatographs and getting them into production, some of them we fought for quite a while trying to get them to stabilize, because you're going for ISO certification on purity of materials supplied. So inside of ISO requirements are a lot of rules, and inside of chemical societies there's these rules that these people follow that aren't magic. So that was my kind of intro to gas chromatography. I'd heard, I've seen, I knew about it, but the intimates, the actual doing of it, learning how to spec a capillary column or the materials inside of it, what capillary columns are made out of, and the amazing science inside of that. These are people, that's all they do is capillary columns, diatomaceous earth separations, and other exotic materials put on the surface of a tube to do separations. Not packed solid, it's just the surface of the tube is enough to do these bindings, because, or this slowdown, these, it's kind of like a pool, no, it's not a pool table. Snooker? I don't know. So, yeah, gas chromatography is one of the ways that you do elemental searches. My instruments didn't have to have sample preparation because we had a range of possible gases that could be seen by the analyzer, so we didn't have to account for other gases. Calibration standards, I helped set up the calibration standards. I set up the things required: high purity hydrogen, ultra high purity calibration standards, liquid helium, so specialty gases, high purity gases. And I changed vendors because of some issues that my instruments showed up with, vendor qualifications or vendor specifications. So these are the conversations you have as a chemical engineer working in the chemical industry. Things that most people probably wouldn't understand. On the good side, when I left, they replaced me with a 3-person contract to maintain those analyzers. That's how much time and effort and maintenance it took to keep those things running reliably across the process. And I had them set out, good run times. But you still had to watch them. You still had to know how to fix them and keep them running, or when to fix them. So cool stuff. A little bit of business life share. Hey, thank you, folks.